Hello everyone. My paper about quantum monogamy was recently published in Quantum Reports, and I want to explain why you need to know about it. This paper is surprising for two reasons. First of all, it demonstrates that quantum monogamy is not a real phenomenon. It is an artifact of human analysis, and therefore quantum cryptography cannot work as currently advertised. Quantum monogamy is essential for device-independent quantum key distribution. So, if it is a subjective post-detection effect, then it cannot have objective effects on remote quanta. In plain language, our quantum code can be stolen without our knowledge. Therefore, we need better protocols, without magic. Secondly, this conclusion about quantum cryptography is based on a new discovery in probability theory. It turns out that some joint measurements can have more than one coefficient of correlation for the same exact record of events. Simply by choosing to consider two properties at a time or four properties at a time, we can get different patterns of correlation for the same two observables. No post-selection or data aggregation is needed for this to happen. Such behavior was simply unthinkable in classical probability theory, but it seems to be the solution for several quantum puzzles. The most well-known thing about quantum mechanics is that nobody knows what's going on. As the saying goes, if you think that you understand it, then you do not. But why is that? One possible explanation is that we live in a strange universe. The laws of physics cannot be understood by feeble human minds. So there is no need to ask any questions because there are no answers to be found. Then again, it is also possible that nature is not to blame. Instead, the problem is that we, the observers, are approaching this subject with mistaken assumptions. In this case, questions are welcome. But then again, what should we question? Well, let us try to work in reverse and maybe we will get an idea. The most baffling aspect of quantum behavior is the so-called process of entanglement. But what do we really know about entanglement? First of all, it became a testable phenomenon with the help of a statistical argument, which is Bell's theorem. Secondly, we always confirm its existence in practice with correlation experiments. So, if there was something to question here, it would have something to do with the rules of correlation. Okay, let us review the basics of this concept. If we want to determine a coefficient of correlation, we begin with a joint measurement. We choose two properties and study their coincidences at the individual level. For example, if we have binary variables, then we can get four types of joint events: plus plus, plus minus, minus plus, and minus minus. Next, we use a predefined formula to compress this data into a single number. For example, we can add up all the events with identical values, such as plus plus and minus minus. Separately, we add up all the events with opposite values, such as plus minus and minus plus. In a nutshell, the data contains two subensembles, one correlated and the other anti-correlated. The goal is to determine which pattern dominates and to quantify this relationship. Accordingly, we can take the difference between the two kinds and divide it by the total number of coincidences. In the end, we can get a value between -1 and +1. The formal way to express this is to say that the expectation value for two observables A and B is determined by this relationship. The important thing to notice here is that we are working with a fixed record of events. It does not matter what happens before detection. Once we collect the coincidences, they cannot change anymore. The pattern of coincidence is fixed. Secondly, the formula for deriving a coefficient is like a deterministic machine. Given a joint distribution, the result is predetermined. There are no degrees of freedom in this formula. Therefore, the outcome is uniquely determined by the data. In other words, there is a one-to-one correspondence between the observed reality and the assigned coefficients of correlation. This has an important implication. Namely, if we repeat an experiment and we get a different coefficient, then the underlying reality is suddenly different too. The only way to get a different coefficient is by changing the physical relationship between pairs of recorded events. On closer inspection, this relationship between coefficients and reality is crucial for the interpretation of quantum monogamy. For example, suppose that we have a source that produces 4 beams of entangled quanta. To make it easier to visualize the process, imagine that all the channels produce identical results if measured in the same way. In this case, all the detectors are active with the setting A, and all of them display a plus result. So, just by measuring one beam, we can predict the outcome of all the 4 measurements with certainty. This confirms to us that we have 4 correlated beams. Yet, this is where the magic begins. Suppose that we choose only 2 of these beams and use them to perform a Bell experiment. As you know, this means that we need to conduct 4 different pairwise experiments. In this case, we need to determine the coefficients for AB, BC, CD, and finally DA. For example, we might conclude that these 3 coefficients are equal to square root of 2 over 2, while the last combination has a coefficient of negative root 2 over 2. If we plug these values into the CHSH inequality, we get a very strong violation. This is typical behavior for entangled quanta. But now we can ask, why do we need to make 4 different joint measurements? We have 4 entangled quanta and 4 properties to measure. Ergo, we can distribute the 4 settings A, B, C, and D among the 4 observers. As a result, we can get all the pairwise combinations in one experiment. Though, what would happen if we did that? Would we still get a Bell violation? Surprisingly, the answer is no. Quantum theory predicts no violation in this case. Instead, it describes quantum entanglement as a monogamous phenomenon. In other words, strong entanglement is an exclusive relationship between 2 entities. We can have 2 quanta that are fully entangled, or 4 quanta that are partially entangled, but we cannot have strong entanglement for more than 2 quanta at a time. Accordingly, if we measure all the 4 properties in one experiment with 4 entangled quanta, we cannot expect a Bell violation. At first sight, entanglement is like a conserved substance that can be redistributed as a zero-sum game between several entities. Yet the mechanism for this process is not so easy to explain. You see, if we measure only 2 quanta at a time, then Alice and Bob get a set of coefficients that can violate the CHSH inequality. On the other hand, as soon as we add the other 2 quanta to the measurement scheme, Alice and Bob must get different coefficients of correlation for the same exact settings. You see, if the coefficients are such that Bell violations are impossible, then they cannot possibly be the same in both cases, at least for one combination. Yet, any combination can be assigned to Alice and Bob in this experiment. Furthermore, as we have just seen, coefficients of correlation are supposed to be uniquely determined by the underlying physical reality. So, if we have 2 types of coefficients for the same pair of measurements, then we must have two different realities or two alternative universes. In one universe, Alice and Bob can violate the CHSH inequality because Charlie and David are excluded from the joint measurement. In the other universe, they cannot because Charlie and David are making simultaneous measurements. Similarly, the quanta of Charlie and David appear to lose their entanglement simply because Alice and Bob perform their measurements no matter how far away. In the final analysis, this is why quantum cryptography is supposed to be fundamentally secure. You see, if Alice and Bob perform a Bell experiment and get a strong violation of the CHSH inequality, then Charlie and David cannot have access to entangled quanta anymore. They exist in a universe where these two quanta are no longer entangled. Therefore, Charlie and David cannot use their quanta to steal the quantum keys from Alice and Bob. When the quanta are created at the source, they are all correlated. Yet, as soon as Alice and Bob get a Bell violation, the quanta of Charlie and David behave as if they collapsed to some kind of an entangled state. Ergo, a separate experiment with these two quanta should not be able to produce Bell violations. To sum up, quantum behavior cannot be explained with classical physics, but this appearance is rooted in our understanding of probability theory. Quantum entanglement is verified with correlation experiments. More importantly, correlation patterns are uniquely determined by the data. The coefficients cannot change unless the underlying reality also changes, and this is why we get quantum magic. Again, we cannot question the link between coefficients and reality. This is why we must believe that quantum monogamy is real. Entangled quanta must change their objective properties depending on the number of joint measurements because the patterns of correlation are different in each case. In the final analysis, this is what guarantees the fundamental security of device-independent quantum key distribution protocols. Though, let us try something different today. Let us question this relationship. Is it always true that coefficients are uniquely determined by the data? The basic unit of any correlation experiment is an act of coincidence. At first sight, we have no choice here. Things happen at the same time, and we get coincident events. However, notice that quantum theory does not predict weird behavior for every possible observable. Entanglement as a quantum phenomenon is fully restricted to the domain of non-commuting random variables. In other words, it is only expected to work for properties that are mutually exclusive. So let us focus our attention on this special case. Suppose that we have a physical system with mutually exclusive properties. These properties coincide, and then... Wait a minute. If they are mutually exclusive, how can they coincide? For example, flour can become dough, or it can become a croissant, but not at the same time. And if these properties do not coincide, how can we get automatic coefficients? As you will see below, the answer is very simple. Coefficients cannot exist without coincidences. And so we, the observers, must find a way to produce artificial coincidences. For example, we can record different properties at different points in time for a single system, or we can make two correlated copies of a system. As it turns out, when we combine incompatible properties across time or across systems, the coefficients of correlation are no longer fixed in advance. Instead, they require observer-dependent input after detection. Therefore, quantum monogamy is not an objective physical process, but rather an artifact of our method of analysis. The potential relationships between properties are systemic and objective, but the correlations are subjective because coincidences as part of a single system are physically impossible. Let us try to understand how this works. Consider a big classical object such as a round table. For this example, we can imagine that the table is spinning under a fixed arrow like in the game Wheel of Fortune. However, I find it easier to imagine that the table is fixed and that the arrow above it is forced to rotate by some kind of mechanism, like a clock. The difference from a regular clock is that we want to study binary variables. Hence, we can choose an arbitrary orientation and say when the arrow crosses this axis pointing up, it will correspond to a plus value. When it crosses the axis in the opposite orientation, we have a minus value. So, if the arrow keeps rotating like clockwork, we are going to have a 50-50 distribution of plus and minus events. Similarly, we can choose other axes and assign binary values in opposite directions. If we choose 4 axes, we can divide the clock face behind the arrow into sectors and label them so that we can conduct a CHSH experiment. For example, observable A has opposite sectors with plus and minus on this axis, observable B on this axis, and so on. Accordingly, if the arrow is allowed to rotate like clockwork, it will express all the observables in sequence. As a reminder, quantum properties are mutually exclusive when they do not commute, and only one outcome per observation, plus or minus, is possible. Yet, after many iterations, all the possible 8 values are realized one at a time in large numbers. This is what enables us to perform a Bell CHSH experiment. We can expect the same type of behavior here in this classical system by allowing the arrow to rotate continuously over the table. Every time it crosses the middle of a sector, we record an event denoting the variable A or B and so on, the value plus or minus, and the time coordinate. If we allow the process to continue long enough, over many cycles, we are going to accumulate enough data for correlation analysis. Fortunately, we do not need sophisticated calculations in this case because the same pattern is repeated over and over. This makes it easy to visualize the relationships between our events. Of course, a quantum Bell experiment requires 2 stations, not 1. We want the measurement stations of Alice and Bob to be very far from each other in order to exclude any communication between them. However, we do not need that here. We have a very big classical system and we know what is going on. The values are written on the table well in advance, and printed symbols do not change when we look at them. Hence, we could have 2 identical tables and 2 arrows that spin at the same rate. We can even place them far from each other, but this will not give us anything that we don't already know. Whether Alice and Bob read the values from 2 identical tables or from one and the same table, the measurement outcomes and the relationships between them cannot change. The rules would be the same if we had 2 identical playing cards. We could ask Alice if the card number is even or odd, and we could ask Bob if the color is red or black. Yet, the degree of separation between them does not matter because no interaction is possible between printed properties. Instead, it is quite instructive to use a single table here because we can see why some patterns emerge and not others. So, let us imagine how this experiment might run. The arrow is constantly moving, and we get a continuous sequence of cyclic events. As the events happen one by one, Alice records the values and timestamps for A and C, while Bob records the same for B and D. However, every event is taking place in isolation. There are no instantaneous coincidences, though we need coincidences for correlation analysis. Consequently, we need to define an extended window of coincidence such that more than one event is included in a conventional joint measurement. Notice I use the word conventional joint measurement because objectively we only have a flow with single events. So, we as observers must follow this order of operations. First, we let the experiment run and accumulate all the data with isolated events. Then, with a full record in hand, we use the timestamps and the chosen window of coincidence to group the events into imaginary bins with conditional coincidences. For example, let us consider what happens if the window of coincidence is large enough to include all the four variables A, B, C, and D. This means that one iteration corresponds to half a period of rotation, and we have two groups of four events per cycle. The record of events can be arbitrarily long, but the basic pattern is the same because we can only have two types of coincidences. In this case, we have two options. The observables can all have plus values in a single window, as seen in the inner ring of this diagram, or they can all have minus values, as shown in the outer ring. This pattern cannot change no matter how many cycles we have in our dataset. It is always the same cycle. Therefore, we can calculate the coefficients of correlation directly without advanced tools. For example, we see that observables A and B can only exhibit plus plus and minus minus coincidences. They will never have plus minus or minus plus combinations. Therefore, they are maximally correlated. To make it explicit, let's use the correlation formula. We have 100% identical values and 0% opposite values. Therefore, the final value of the coefficient is plus 1. The same exact pattern is seen for the remaining three combinations. Therefore, we have four coefficients with the same value. If we plug these four values into the CH-SH inequality, we get the modulus of 1 plus 1 plus 1 minus 1. So the final result is 2 in perfect agreement with the so-called classical prediction. However, Bell experiments are usually conducted with pairwise joint measurements. So let us make our window of coincidence small enough to include only two consecutive events. Again, we have the same recurring cycle of 8 events, but this time we divide the flow into 8 overlapping pairs AB, BC, and so on. In other words, we use the same flow of events as in the first case, but this time we are not looking at 4 outcomes at the same time. Instead, the events are directly paired according to their ability to fit into the new window of coincidence. This means that we no longer have two closed cycles of possible connections between events. Instead, when we compress the 8 events into a diagram with 4 observables, we obtain a Mobius strip. Just like before, one full rotation of the arrow produces 2 cycles of 4 events. This is what we should expect given that we have binary variables. Yet, this time we have a continuous double loop instead of 2 disconnected simple loops. Just like in the previous example, the same cycle is being repeated continuously. Therefore, the pattern of detection does not change over time. We can look at this diagram and immediately determine the coefficients of correlation. As you can see, A and B can only coincide with correlated events. plus plus, and minus minus. This means that they have the same coefficient of correlation as before, which is plus 1. Similarly, BC and CD display the same behavior and have the same coefficients of correlation. However, notice that D and A combinations are no longer the same. Instead of direct lines along the two loops, we have a crossover. As a result, the only possible combinations here are plus minus and minus plus. In other words, we have perfect anti-correlation. The coefficient of correlation is minus 1. So, if we plug these coefficients again into the CHSH inequality, we get 1 plus 1 plus 1 minus minus 1, which gives 4. Obviously, 4 is not less than 2. Not only do we have a Bell violation, but we also have a maximal violation, which is known as a superquantum result. This in itself is very interesting from a theoretical point of view, but this is a topic for a different discussion. In conclusion, a simple choice between counting 2 properties at a time or 4 properties at a time leads to radically different outcomes, even though all the events are the same and their recorded order is also the same. Though, how is this possible? Let us take a closer look at these diagrams. When we decided to count 4 observables at the same time, we divided the data flow into groups of 4 events. So, all the pairwise coincidences must be treated as subsets of these quadruple coincidences. This means that 3 of the 4 combinations are paired with their closest neighbor in time: AB, BC, and CD. In contrast, A and D can only be combined at a distance, because they cannot be adjacent in time as part of their group. On the other hand, if we enable pairwise combinations with no regard for collective consistency, then any 2 events can be connected to their closest neighbor in time. In particular, A and D get to be connected with events that belong to different coincidence windows in the previous pattern. This is why the net behavior of the system is suddenly different. In short, 2 different patterns of correlation emerge from the same record of events, but there is nothing magical about this phenomenon. This is just a combinatorial effect, plain and simple. In a way, the most surprising aspect here is not that we have such a drastic change in the pattern of correlation, but rather that it took so little to achieve it. When Bell violations are interpreted with action at a distance, it seems plausible that every Alice event is somehow perturbed by Bob's measurement. For the same reason, when we have quantum monogamy with radical changes between entangled and non-entangled behavior, we expect all the coefficients of correlation to be affected. Yet, as we saw, it is not just enough to achieve this transformation with a single coefficient. Instead, it might only be possible to achieve such transformations with minimal reorganization. For example, let us assume that we have a classical pattern, like in the first example, where all the coefficients were equal to plus 1. Then, let us assume that we rearrange the sectors on the table and that all the coefficients are now flipped. So, instead of 4 coefficients that are equal to plus 1, we now have 4 coefficients that are equal to minus 1. In this case, if we plug all the coefficients into the CHSH inequality, we get the modulus of minus 1, plus minus 1, plus minus 1, minus minus 1. Yet the net effect is that we get the same result at the end without a Bell violation. The sum is equal to 2 again. Instead, when we look closer at the CHSH inequality, we see that we can only violate it with incompatible coefficients, just as we did with pairwise coincidences. 3 coefficients need to be positive, while the fourth is negative, or vice versa. Please note that such a combination is perceived as impossible in classical probability theory. That is because classical spaces are usually defined for permanent objective properties. For example, this card has color, suit, texture, it can be odd or even, and so on, all at the same time. So, when we try to determine the coincidences, we have objective restrictions. Let us suppose that we printed a special deck of cards where 4 properties on each card are strongly correlated. Hence, if property A is plus, as seen in the inner circle, then B is also plus. Or if A is minus, then B is minus. Similarly, we get the same pairings for BC and CD. Yet notice that we have already written down all the values for the 4 observables after checking only 3 pairs. Therefore, we are not free to combine the fourth coefficient in some arbitrary way. If 3 coefficients are plus 1, then the fourth can only be plus 1 as well. As a result, Bell violations are impossible. In contrast, when we have mutually exclusive properties, the structure of coincidence is not a priori established. Instead, we are free to create artificial subjective coincidences. More importantly, if we choose to make pairwise combinations, we can obtain incompatible coefficients with Bell violations. On the other hand, if we force the simultaneous consideration of 4 observables, then we erase this ability. So, when we measure 4 properties at the same time, we automatically get compatible coefficients without Bell violations. Intuitively, this feels like a drastic change. Yet, as we saw above, this is possible with just a simple change in the size of the coincidence window. With this insight in mind, let us go back to the problem of quantum monogamy. In classical probability theory, we assume that all the properties of a physical system exist at the same time. Therefore, they have an objectively predetermined coincidence structure leading to unique coefficients of correlation. As a consequence, any change in the coefficients of correlation must be explained by a change in the underlying physical reality. For example, Alice and Bob measure 2 quanta at a time and achieve a Bell violation. Yet, when they measure the same observable in coincidence with Charlie and David, they cannot get violations anymore. The observation is that we have different coefficients of correlation for the same 2 measurements of Alice and Bob. The implication is that physical reality is different. Therefore, when Alice and Bob get a Bell violation, they infer that Charlie and David cannot have entangled quanta. Yes, all the 4 quanta were prepared to be correlated, but now we seem to have evidence of fundamental ontological change. Therefore, it seems that quantum cryptography is fundamentally secure. Charlie and David cannot possibly use their quantum bits to steal the secret keys from Alice and Bob. In any case, this is the current interpretation. In contrast, we have just seen that mutually exclusive properties do not have a well-defined coincidence structure. At least 2 patterns of correlation are possible for the same record depending on how many measurements are considered at the same time. More importantly, these conditions can be applied entirely after detection without changing the dataset in any way. Again, we expect Bell violations for pairwise measurements, but we cannot have them for quadruple measurements. Yet, this is entirely a combinatorial effect without any associated changes in the underlying reality. Therefore, Alice and Bob are free to measure their quanta in isolation or in coordination with Charlie and David. They get the same exact detection events in both cases. Instead, the switch between entangled and non-entangled behavior emerges as a post-detection effect. Therefore, a Bell violation for Alice and Bob does not entail any remote effect on the objective properties of the remaining two channels. Alice and Bob can get a Bell violation in isolation from Charlie and David. Yet in principle, these two channels can also produce Bell violations as long as the two pairs are observed in isolation from each other. Therefore, quantum monogamy cannot guarantee the security of quantum cryptography. The main conclusion here is that quantum monogamy is not really a quantum phenomenon. This is a natural property of incompatible observables in general, be they classical or non-classical. As we have just seen, the switch between the so-called entangled and non-entangled correlations has nothing to do with objective reality. It is just a combinatorial effect. Previously, this possibility was not known because of the expectation of unique coefficients of correlation in classical probability theory. In the past, conditional correlations were only possible with major changes to the data, either by down-selecting subensembles or by combining different samples into one. In contrast, here we saw that mutually exclusive properties cannot coincide. Instead, coincidences require additional conditions that are introduced by the observers after detection. In other words, this puzzle is not caused by the weirdness of Mother Nature, but rather by the limits of our knowledge. Specifically, we can see that classical probability theory was not suitable for the analysis of classical physical properties that are mutually exclusive. To sum up, we have just shown that quantum cryptography, as currently understood, is not fundamentally secure. Device-independent quantum key distribution protocols are explicitly placing their faith in magical interactions. They treat quantum monogamy as if it was unquestionably an objective phenomenon. This was a very popular assumption for a long time, but it is nonetheless ungrounded. On the other hand, this demonstration does not prove that quantum cryptography is fundamentally insecure as a matter of principle. The goal of this presentation is simply to raise awareness about the limitations of current protocols. Indeed, a better mechanical understanding of quantum behavior should lead to more secure cryptography, because we can design truly reliable protocols with justified ontological assumptions.